Okay, it's 9:55. Let's continue. Resume the recording. Okay, now I want to explain a little bit on equation, derivation. Okay, you have gone through the video lectures, how to do derivation, and basically you have also tried. You have completed some exercises as well. So I just want to highlight some of the important points. Okay, so there are basically two important fundamental formula equations you need to start with when you do derivation, right? So basically we want to derive equation for heat transfer rate, Q, and also temperature gradient, right? So for Q, heat transfer rate, we will start from Fourier's law. This is Fourier's law, right? So Qx per A equals to negative K dt over dx. So this is the basic formula. A, what is A? A is actually the cross-sectional area normal to the heat transfer direction. Okay, this one you must bear in mind. A is what? A is the cross-sectional area of the part, okay, which is normal to the heat transfer direction. You know, here you see heat is being transferred from x0 to x1, right? So this A is actually the area normal to this direction, 90 degree. Okay, so this is very important. What else? Temperature gradient, distance, right? Dx. So that's why this A is different, depends on the geometrical shape, right? So that's why you learn for flat plate, for cylinder, right? And also for sphere. Okay, then another equation we refer to is energy balance equation, right? We use that for deriving equation for temperature profile. Okay, and you were exposed to three types of coordinate system, right? Cartesian, this one we are very familiar with. The typical one, the X, Y, and Z axis, right? Three-dimensional. Okay, then you also we also refer to cylindrical coordinates, right? So for this case, okay, I explain to you what is all this coordinate first. So this is the cylinder coordinate system. Okay, so it contains three components you see here. Okay, this rho is actually the radius, right? Then the phi is actually here. It moves like this, right? Z is the vertical, it's like the Cartesian Z. Okay, so this cylindrical coordinate and spherical coordinate, they also three components. You see, R is the radius component and theta and also phi. Okay. Okay, so when we do derivation, there is one very important assumption, right? Which enable us to simplify the whole derivation process. That is, we assume heat is being transferred through one dimension, in one dimension only, right? So you see, I give you an example for Cartesian coordinate. So when we say heat is transferred through one dimension only, what does it mean? Let's see this cube. Okay, let's take this cube as example. Okay, let's say heat is transferred from inside to outside. Okay, inside to outside from all surfaces. Okay, so what you see, this cube can actually be broken into 6 surfaces, right? So what does it mean by heat is transferred through one dimension only? It actually means, let's say, if you refer to okay, if you refer to the yellow surface, okay, the yellow surface 1, 2, right? Okay, yellow surface. So so when we draw the cross-sectional area, it looks like this, right? This is okay inside. This is outside, right? Or T out lah. Okay, so heat is being transferred inside to outside. Okay, so what does it mean by that when we say it's one dimension? It means we assume heat only transferred through, in this case is what? If you refer to this coordinate system, in which direction? X, Y, or Z? Is
X.
Y. Is Y direction, right? Okay. Actually, in actual situation, heat also, let's say, it can also move upward, right? It can also make our jobs easier. We set this assumption. We assume, okay, heat is only transferred through one direction only. Okay, meaning all parts, it will move like this only. Okay, from left to right. Okay, but in actual situation, it can move in all direction, right? So, because if we don't make such assumption, you see, you need to consider X, you need to also consider Y, you also need to consider Z, right? Okay, let's say there is no heat generation. Let's say there is no steady state. Okay, so it becomes 0. But you still have this part you need to solve. So can you imagine you need to solve this type of PDE, right? Partial differential equation. How difficult is it? It is. Okay, so if we assume it is only heat only transferred through one direction, okay, in this case, it's Y only, right? It's Y only, then the whole derivation process will become much easier. Okay, that's the purpose. Okay, so, and let's see, the same thing actually applicable to let's say now we see these two surfaces, 1, 2, right? If we draw it, the cross section, okay, then heat transferred, let's say we take this plate, this one, okay, from inside to outside. So heat is transferred. If refer to this coordinate system, then this is x direction, right? So we assume heat only move from left to right, from point number 1 to point number 2 straight. But in actual situation, it is not in that way. It moves to all direction. Okay, just that engineers normally we make things simpler so that the whole process can be faster and easier. Okay, we can simplify the formula, then the calculation process will be much shorter. Okay, that's the purpose. Okay, same goes to these two. Okay, the top and bottom. Okay, so when we say heat transferred through one direction, so it means it's only through z direction. Okay, this is the meaning of heat is transferred to one direction. Okay, this one I will explain later. Let me delete all this first. Okay, actually same thing. Okay, same applicable to cylinder and also sphere. When we say heat is transferred through r direction only, we are saying that heat is only transferred through r direction. Okay, it doesn't transfer through this direction and z direction. Okay, why? The same purpose, to make our derivation process simpler, save our time. Okay, and it will lead to acceptable accuracy. Okay, the derived equation will still give us certain, how to say, acceptable accuracy, although it is not 100% accurate because we simplify some of the parts. So meaning there are some factor we don't put into consideration when we do the calculation. Okay, so the answer will not be 100% accurate, but the accuracy is acceptable. Okay, for engineering calculation purpose. Okay, same goes for spherical system. Okay, we assume heat is transferred through one direction, that is r direction only, meaning through the radius. Okay, not in all directions, so that the whole derivation process becomes much simpler. Okay, that is the meaning of heat is transferred through one direction. Okay, and next question is, another assumption is the system is in steady state. Okay, what does it mean by steady state? Have you learned this, steady state?
Yes, Doctor.
Okay, yeah, Liang Hong, can you explain? What does it mean by a steady state?
Steady state is actually a condition where the heat transfer, there's no net heat transfer to the object. Means that the heat transfer in equals to heat transfer out, not necessary to be zero.
Okay, okay, correct. Then what happened to the temperature? Let's say if this system, you see a pan on a stove, right, is being heated by the flame. Okay, what, let's say here is T. Okay, when what you can say at steady state, what can you say about this temperature? And what can you say about this temperature?
T1 will eventually T1 and T2 will eventually increase definitely, but until a certain temperature, the temperature gradient will become constant, so they won't change anymore according to time. The del T will equals to 0, become constant.
Okay, under steady state, T1 will change or not? And T2?
No.
Okay,
They
correct.
will change. Yeah.
Okay, correct. Steady state, it means delta T over time, okay, over time is 0, meaning no change of temperature in accord with time. Let's say if this system is at steady state, okay, if this system is at steady state, yeah, and you record the temperature, okay, at T equals to 0, T1 is, let's say, 500 degrees Celsius. Okay, T2 is 50 degrees Celsius. After 1 minute, you record again, T1 still remain at 500 degrees Celsius. T2 still remain at 50 degrees Celsius. When T equals to 60 minutes, 1 hour, you will still get the same result. Okay, if you get this, it means the system is at steady state. Steady state means for our case lah. Okay, one of the aspect on how we see that is no change of temperature over time. Okay, and of course, just now what you say is also correct, right? How much heat in equals how much heat out. Okay, thank you. Now I want to come back here for some of the important things which I think I need to tell you. Okay. Because I see there are some questions, right? Okay, let's take this example. This is question number 5 in your assignment 2. Okay, question number 5 in your assignment 2. I see different version of circuit diagrams. Okay, let me show you different version of circuit diagram. Can you see what I'm sharing now?
Yes, doctor.
Okay, you see this answer by group 1. Okay, their circuit diagram is very simple. Okay, this is their circuit diagram. Okay, only 2 components, R1 and R2. R1 is R for conduction, R2 is R for convection. Okay, let's see for group 2. Okay, you see another version. Okay, there are 6 resistance and 3 resistance here. Okay, for group 3, let's see. Also different, right? 6 plus 6. So which one is correct?
I personally prefer group 3 one.
What about the rest? Okay, my answer, my opinion, group 1, this circuit diagram is correct. Group 3, this circuit diagram is also correct. Okay, but if we want to go to the very fundamental, actually group 3's circuit diagram is more accurate, I would say. But I don't understand group 2. Group 2, is there anyone from group 2 here? I don't understand why it becomes 3 after this. Could you please explain? Group 2? Anyone from group 2?
Yes, Doctor.
Yeah.
Also,
Why these two become 1?
actually, we prefer similar to the group 3 one, but at that time we quite confused, so do it like this. But the M we want to do is similar with the group 3.
Okay.
Total, actually, I think I understand why they do like that. They just combine the area, I think that's for A or something. So the area is the same. They just combine it into R1. And later maybe times 2, I think.
Yeah, just that it confuses people. Okay, it confuses people. It's not tally with what we understand from them. Okay, I want to explain to you how to construct this. Why I say this is correct and this is also correct. Okay, actually I prefer this lah. Okay, this one actually it shows the very fundamental circuit diagram. Okay, you see, there are 6 surfaces, right? There are 6 surfaces. This ice box, right? 1, 2, 3, 4, top and bottom, 6. Okay, there are 6 surfaces. So, heat is being transferred from outside to inside because temperature outside is higher than inside. Inside is ice, right? So that's why here first is the convection, right? Then after that is conduction. Okay, so it's very simple to understand, right? Because there are 6 surfaces, so that's why heat is being transferred from outside to inside through 6 different surfaces, right? 1, 2, 3, 4, 5, 6. So that's why, and the heat transfer plus heat is being transferred through the 6 surface at the same time, simultaneously, right? So that's why you need to divide into 6 parts. Right? But if the situation is, let's say, like this one I give you already, right, last time. 1, 2, 3, 4, 5, 6. If ice is here, okay, let's say if ice is here, and this is 25 degrees Celsius. Then it is like this, right? Series. But here, since heat is transferred from outside to inside through 6 different surfaces at the same time, it's not passed by one surface then after next surface, right? All at the same time. That's why 6 surface, right? Okay, so this is the basic one. Okay, is correct.
Actually, Doctor, I have a question for this question.
Let me finish my explanation
Okay. Sorry,
first.
sorry, Doctor.
Okay, so you see, actually what group one did, I'm not sure if group one you understand what you did. Actually, what you did is you sum up everything, right? You sum up why you can do this. Okay, because the thickness of all the surfaces are the same. If the thickness of the surface is different, then this is wrong already. Okay, let me show you. Let me show you the basic equation. Okay, this one. This is summary, right? Resistance for plate. Okay, R for plate is x1 minus x2, this thickness lah, divided by A and K, right? So just now, group one, you sum up everything, okay, as two resistances only, right? This is number one is for convection, number two is for conduction. It is correct because how to say, coincidentally, the thickness of all the surfaces are the same. Okay, but if the thickness of the surfaces are different, then your circuit diagram is already wrong. Okay, why? Because they have different thickness. Okay, so that's why I say circuit diagram by group number 3 is the safest. But of course, if you understand the concept, actually you can simplify the whole circuit diagram into this. Then it makes your calculation work much easier. Okay. So let's see here. Okay, if I change the question, the wall thickness, okay, not 5 for all, but for the side is 5 cm, for the top and bottom is 2 cm. I want all of you to try now, okay, how does the circuit diagram look like? Okay, I give you 2 minutes. Construct a circuit diagram for this system. Now the wall thickness is different already. Okay, for the side is 5 cm. For the bottom and top are 2 cm. Okay, meaning 1, 2, 3, 4, 5 cm thickness, but top and bottom thickness are 2 cm. So, can you show me your circuit diagram? Okay, don't worry, I won't ask you to show. Okay, but let's try to do it together. Can you see my slide?
Can Doctor?
Yes, doctor.
Yes, doctor.
Okay. So in such a case, now you have 4 surfaces which are the same with same thickness, right? Let's see. You see the basic formula for R is x1 minus x2 per A. Okay, let's take this. Okay, R delta x per A K, right? A different is okay, right? Because A you can just calculate, right? You can just, but X, okay. So in such a case, initially you should have 6, right? 1, 2, 3, 4, 5, 6, right? This is like group number 3, right? Circuit diagram of group 3. Here you have T out, T in, which is 0. T out is 25. So these are for convection. Convection R equals to 1 over A H, right? So all these. Okay. Then here you have R for surface A, let's say, equals to, let's say A, B, C, D are for sides. E and F are for top and bottom. Okay, so A is 0.05, right? Because 5 cm and AAK. Okay. B is also 0.05 AK. Same goes to RC, same goes to RD. Now RE is different because it becomes 0.02 over AK. RF also 0.02 over AK. Right? So this is the correct, most fundamental circuit diagram. Right? The rest, I believe this part you understand. Okay, but I can actually simplify it. Right? I can simplify it. It can become like this. If I understand the concept, now I know. Right? It can actually be simplified because 1, 2, 3, 4, they are actually the same. Right? Just that now the A different, right? So, but the delta X is the same. So A, actually I can add them all. They can become 1, right? So I can actually simplify this circuit diagram becomes 2.
Sorry for disturbing, doctor.
Yes?
The recording button.
Okay, sorry. Sorry. Thanks for reminding. Thank you so much. Okay. T naught, T in, T out, right? 0 is 25. Okay, so this is convection. This is conduction, right? So convection, I don't see so much, but conduction you see. So you can actually combine these four, right? They'll become R for site. R for site equals to, because they all have the same thickness, so they can be combined. But now the A is a different A. This A is what? AA plus AB plus AC plus AD. This one here is AA, this AB, this AC, AD. Okay? And number 2 here. These are what? Our top and bottom. Top and bottom, right? Equals to what? Thickness is 0.02, so that's why they can be combined together. Here is A for top and bottom, right? Okay, so this A for top and bottom is what? Equals to AE plus AF. Okay, so actually these two are the same, but if you understand the concept, you draw this, it saves your time, because you don't need to calculate all this one by one, then you spend so much time. Okay, yeah, so that's why just now, if all the wall thickness are the same, I said group number 1, their circuit diagram is correct, right? Because they combine everything, right? Let's say now all wall thickness are equal. Okay, all are 5 cm. Then actually it can be simplified, becomes like this. R convection, R conduction. R conduction equals to what? Equals to 0.05, because all the thickness are the same. And A is A total, right? Okay, A total equals to what? A total equals to AA plus AB plus AC plus AD plus AE plus AF. Total surface area. Then this is correct. Do you get the concept? Okay, I hope you get the concept, yeah? Okay. Now, let's recall the question I asked last time in group activity 2, I think. Okay, let me clear this board. This board. How to clear. Okay, you still remember the question last time where we start, right? There is a container, consists of cylinder and also 2 hemisphere, right? Contains oil inside. Okay, T surface, T of the inner surface is 400 Kelvin, and T outside is how many? I can't remember. It's okay lah, T out lah. Okay, so heat will be transferred from inside to outside from all direction. So how does the circuit diagram look like? Okay, so if you use the same concept, okay, you understand why there is parallel. Okay, there are now 2 parts, actually 3 parts, right? Part number 1 is what is that? Part number 1 is cylinder. Part number 2 is hemisphere 1. Part number 3 is hemisphere 2. Right? Okay, let's see the very basic. Okay, the very fundamental one. Okay, this is T in 400. Okay, you see, heat is being transferred from inside to outside, from the oil to the outside air simultaneously, right? From all these 3 parts. So that's why you need to divide here, right? That's why it's parallel. So here, what is this? This is R for hemisphere 1, right? And this R for hemisphere 2. Let's say this is hemisphere 1. This is hemisphere 2. And this is cylinder, of course. So this is R for cylinder. So what is R for hemisphere? What is R for hemisphere? You only have R for sphere, right? And how this formula is derived? It assume, let's see this. Okay. Where is it? Let's see. Okay. So you see Q. When it is derived, what is the air used? The air is air for sphere, the whole sphere, because the formula is 4 pi r squared. This is for one whole sphere. But now your case is what? Hemisphere, right? So there is some modification you need to do here, right? Because this is for full sphere. And now your case, this is hemisphere. So what you can do, the formula is 1 over pi and 1 over r1 minus 1 over r2 divided by 4 pi k. So you need to have 1 over r1 minus 1 over r2 divided by 4 pi k. You need to times half, right? And same goes to this. R over R1, R over R2 for pi k, and also half, because all these are hemisphere, right? And this is what? Cylinder is ln R1 per R2, 2 pi lk. So R cylinder is ln R1 over R2 divided by 2 pi lk. Okay, sorry ya. Continue. Okay, and this is R for convection. Okay, for convection and for convection. Okay, and this is outside temperature, right? Okay, and actually this, if you understand, this can actually be simplified, right? How to simplify it? Because we know these two are actually the same, right? So we can actually make it like this. Only 2 parts. Meaning the first part is for sphere. The second part is for cylinder. So this is R for sphere equals to 1 over R1 minus 1 over R2 divided by 4 pi k. There is no half anymore because you combine already, right? And this is R for cylinder. It remains the same, ln R1 over R2 divided by 2 pi L k. And this is R for convection, R for convection. You know. Okay, and do you know this can, if you want like group 6, they further simplify it because they want to show they really pandai. Okay, so their circuit diagrams become like this. Okay, this is T out, this is T in, this is RS, this is R cylinder, and this is R for convection. Okay, what's the difference? Okay, here R for convection, R convection for sphere equals to what? 1 over A sphere H, right? And this is what? R for convection for cylinder, right? R convection for cylinder equals to what? 1 over A cylinder H. Then, if you simplify, it becomes like this. This R convection becomes what? Become 1 over A sphere plus A cylinder times H. So, you will get the same answer. Do you get what I'm trying to say?
Yes, doctor.
Yeah. Any question? So if you understand this concept, then any question we can solve, no problem. If you understand the concept of how to construct this circuit diagram, then you understand, then any kind of question you can solve, no problem.
For the ice chest, I have one last question, doctor.
Okay, what's the question?
Actually, when I doing this R right for the surface, I don't really understand why the air we should use the area. Why we should use the inner area, not the outer area?
Okay, let me tell you. Okay, that IHS question actually is a little bit complex. Okay, let me see if is there anything important I want to explain to you, because before I answer your question, let me see, because I think there is something more important. I'm afraid I missed out something very important. So Liang Hong, wait. I let me check if there is any feedback I want to give to you before I proceed to answering your question. Okay, I want to give feedback on Padlet. Okay, thanks. Can you see what I'm sharing now, Padlet?
Yes, doctor.
Can you see the Padlet? Okay. There are a few things. First, group number 5. Is there anyone from group number 5 here? Group number 5. Anyone? Group number 5? You haven't done checking. The deadline is actually yesterday. May I know what happened to you? You can contact me later. Okay. I'm just curious why you didn't do the
Hi,
evaluation.
Doctor, can you hear me?
Yes.
Doctor, I'm from group number 5.
Mm-hmm.
Actually, I think we forgot to upload the question. We have checking and we list out the question and the comment. And sorry, forget to upload our question and the comment.
Okay, you can do it later.
Okay, thank you.
Yeah, just curious. Thank you for your clarification. Okay, for group number 8, anyone here? I see that, let me see, group number 8, you should comment for group 7, right? Let me see. Oh, okay. You just added, right? Is it? Group number 8, I think these 2 comments were added just now, right? 1 minute.
Yes, doctor. I'm from group number 8. Yeah, the
Just added, right?
comment is just added. Yeah.
I was about to ask why you didn't comment question 1 and question 2. Okay, so since you have added, then okay. Guys, I want you to go through all these comments and questions. Then I want you to respond to all these comments and questions. Okay? Go through this, the comments and questions given by your evaluators, and I want you to answer their question and comments. Okay? This is your homework lah, huh? So I want to see communication. I want to see interaction between you all. Okay, I guess regarding the Padlet, so this is what I want to do. Okay, let me see. Is there any important thing I want you to understand before I proceed to the last part, answering the question? So by far, I think I have told you 2 very important points lah. Number 1, you should be able to explain like how conduction, convection takes place. You should be able to explain. Okay, so all those phenomena you should be able to explain lah. Then number 2, you should be able to master how to construct circuit diagram based on different situations. Okay, so because when you understand the concept, then you should be able to come up with the correct circuit diagram. Okay, you might be tested in the test. Okay, let's say for example, I will give you, I don't know, like this cube, maybe different thickness, right? Or I give you cylinder plus hemisphere, right? Different radius. Okay, so that your understanding can be tested. Okay, so this is very important. I want you, if you still don't understand how to do that, ask us, ask your friends. Okay, most of you are in the campus now, so you can interact with one another, right? And you can gather, discuss. If there is any problem, you can approach us. Make sure you understand the concept of this circuit diagram. You know how to construct circuit diagram. Okay. So now, before we end, actually, if you want to go, you are free to go, because now I want to answer a question raised by Liang Hong just now. Okay, regarding the surface area. Okay, I understand it's a little bit confusing. Okay, because the shape, because I think I share your friend's punya drawing is better. Wait. Yeah. Okay. Yeah, group 2. The drawing is quite nice. Okay, good job. Okay, you see this case. Okay, actually there is thickness, right? So inside contains ice. So the problem with this question is there are some parts. It's difficult to determine the surface area. Okay, you see this part, the part which I am now, we call that, I'm now lorotkan. Okay, this part. Okay, actually all this part because it has a thickness, right? Including this part, right? The side all this area, should this area be considered as heat transfer area? Because it's through conduction, right? Conduction, and we know ice is inside, right? So there is one part, this thickness, the side. Actually, this is difficult to say these parts involved in the conduction, right? Liang Hong, that's what you want to ask, right?
That's one of my guessing at first also. Like the side of it maybe is like
all this part actually, like, because conduction is because the ice inside only cover this area. Let me change the color. The ice only exposed to this area, right?
yeah, total, I understand. It's like the directly surface outside the inner surface.
The ice only in contact with the blue area, right? Not with the red area, because the red area is the side, is the thickness, right? So that makes the whole question difficult. Actually, this is something advanced. If you refer to your textbook, there is actually another method. You need to use numerical method to solve this problem. But we just simplify it. So that's why your assumption is important. Okay, there is, you need, in order to consider this red part, right, you actually need to use numerical method. Okay, which is not covered in this course. So that's why assumption is important. When you give your solution, you must state clear your assumption. What is your assumption? Right? You can assume, you can say, it is assumed heat transfer only occur through the blue area. And let's say, if you want, let's say for convection, because convection is outside, right? So you can say for convection, the whole outer surface is assumed to involve in convection. But for conduction, only the blue area involved in conduction. Do you get what I mean?
Yep, total, understand.
So your assumption plays very important roles. Assumption. State clearly your assumption. Okay, so in high school, you have this idea there is only one correct answer, right? In high school, this is the idea you have. There is only one correct answer. But now you are in the university, okay? You are being exposed to the real world question, the real industrial question, right? So there is no longer like only one single correct question. You must aware of this. You must realize, okay? There is no one single only correct answer. It actually depends on your assumption. It actually depends on how you derive the equation and all the assumption you make when you derive the equation. As long as you are able to explain clearly what is your assumption, okay, you are able to derive correctly, you are able to state your assumption clearly, no one can say you are wrong. Okay, because this is the real world situation. Okay, so I want you to get rid of this kind of mindset. The mindset is there is only one correct question. No. In real world, no, this is not the case. Okay, it actually depends on your assumptions. Okay, so don't be afraid when your answer is like a little bit different, right? If you understand your assumption, then actually, I would say, you won't get zero. Okay, yeah, that's what I want to tell you. Okay, I guess that's all. If there is no more question, it's close to 11 p.m. already. So then I guess we can end here. Coming Sunday, we are going to enter topic number 2, convection. Okay, so we will tell you what to do lah. Yep. No question anymore, right? Okay, then I think we can end here. Thank you very much. Have a good night.
Thank you, Doctor. Good night.
Thank you,
Okay.
Doctor.
Welcome.
Thank you, Doctor.
Doctor.
Thank you, Doctor.
Okay.